здесь самые стойкие, самые заинтересованные, я так понимаю. Вот, это хорошо. Именно для вас это все организуется.
Сегодня первый день весны.
Правда? С чем вас и поздравляю. Вот. Хорошо, спасибо. Пока не наступило 8 марта, хотя я так понимаю, что настроение праздничное, предпраздничное. Мы еще поработаем пару дней активно, а потом можно будет и расслабиться немножко. Хотя нет, на физтехе не расслабляют, не дают расслабиться. И это правильно. Хорошо. Значит, сегодня мы тогда немножко программа у нас сдвинулась, вы помните, вчера немножко мы перебрали по времени, поэтому сегодня будет вторая лекция Achille Stocchi, профессор из Парижа, вчера я представлял, не я представлял его, еще является к тому же и директором LAL. Это он скромно умолчал. LAL — это большая лаборатория линейных ускорителей, там же в Арсе, соответственно, предприятие. И большой энтузиаст Ukrainian Friends Corporation, especially друзья, большие друзья, очень большой круг Украины. Да. Ну, вы это уже почувствовали сами. Хорошо, значит, сейчас будет вторая лекция по слабым взаимодействиям, weak interaction, basic interaction. Самым удобном для вас уровне. Хорошо. Да.
Большое спасибо,
Друзья, дорогие друзья.
Дорогие друзья. Окей. Доброе утро, everybody. Here is the success. Okay, so today I try in about 45 minutes to introduce you on weak interaction. So the idea was yesterday on this line we introduce, we made the introduction, then Marie-Hélène did, I did a little bit about electromagnetism, just to introduce the concept of interaction. Marie-Hélène spent 2 lectures on strong interaction, and then I do it one on weak interaction to prepare the lecture of Sergei, which will follow, on modern development of weak interaction in favor of physics. And then finally Stefan will give 2 lectures on standard model. So this is a sort of also preparation of that. So on next slide I'll okay, so just again I had some question yesterday from you, I think, and maybe I found this way maybe one of the best way of introducing in the simple possible way the weak interaction. That is said, in fact, when you want to understand the weak interaction, I mean, I show you, I mean, that there are, if you look at the different particles, you can see the different particles has different lifetimes. And then what I said yesterday, that different lifetimes somehow shows, because someone, I think it was you, Bob, or another person, asked me, but I mean, why different lifetime, what for another person, why, I mean, lifetime is important to know. I mean, and why we should know, very important to know lifetime, what is giving us as an information to know about lifetime. So I try just to show you that in fact, by looking at that, you can see at the different interaction. Just to see, no, was your question, I think, on that. So you see, I explained you yesterday that the particle which has lifetime of 10 to the minus 23, in fact, we do not access directly by lifetime, but by their width. Then there are other particles which has a sort of intermediate lifetime, which is more electromagnetic interaction, and then a lot of particles which decay with what we believe, what we say, long lifetime, which are more weak interactions. So just to set up the stuff, okay, yesterday I introduced quite quickly the fact that you can measure cross-sectional width, cross-sectional interaction of decay width, in terms of something which is a terms which which in fact a condensation of the phase space, I mean the number of configuration, number of decay of the number of configuration you have after your collision, and some part which you make all the calculation, which is the matrix element where in fact you code your physics. Okay, if you look now with the modern, so I will come back, then I will start from the beginning of the weak interaction. For instance, you look really at interaction like that. I mean, interaction today in our modern language is just, for instance, you take a quark, the quark transform, okay, forget that I forgot some bar, I mean 2/3 going to minus 1/3, emitting a W minus, and then going to electron. So this is really a way you see interaction. So you see interaction in terms of Feynman diagram is that you have external branches, and then also you have a coupling. Okay, this coupling is in fact normally, and this we will see also in the lecture of standard model, you describe interaction in terms of the coupling. The coupling of electromagnetism is alpha 1/137. The coupling of strong interaction, Marie-Hélène showed you yesterday, and this could be eventually the coupling of the weak interaction. So an interaction is characterized by its coupling. Okay. So of course, as I showed you, when you do, if you are a theorist, you make calculation. You calculate, for instance, the decay, the differential decay, or you integrate over the polar angle and you get the decay width. Okay? So decay width depends on the interaction and depends on the strength of interaction. You see that in fact gamma depends on the interaction, on the matrix element. So depends on the coupling. So as large as the coupling is, as large as the width is. But as large as the width is, as short the lifetime is. Okay? So this is the way. I mean, simple way. I mean, so when lifetime is very short, means that this coupling is strong. When the lifetime is short, means that this coupling is small. So weak interaction somehow weak means that you are weak, and you need more time to go to decay, or your cross section is small. Okay, so I think if you can just catch that is quite important. I mean, any interaction could be described in terms of cross section and width. Both are proportional to space and what really matters interaction, and these are proportional to the coupling, and so at the end you see that in fact this is giving us information on lifetime, give us an information on the kind of interaction. So somehow, if you want just to have a first idea, also this is big with the hands, but if you want to have an idea, you take for instance this particle, which is going to proton pi, which is a resonance, and you say that this is 10 to the minus 33. Then you go to a similar decay, which is a part. So these two particles maybe doesn't tell you much to you, but these are particles which are very sigma and this very close in mass, like about 1.3, 1.4 GeV. And they are almost decaying in the same modes. Proton is the same mass as the neutron, and pi on pi. So as far as space phase is concerned, they are very similar. I mean, more or less similar mass particle going to similar decay product. But you say that there are 13 orders of magnitudes between the two in terms of lifetime. If you make the ratio, you get that, but this somehow is proportional to the inverse of the ratio of coupling, that you can call it strong in this case and weak in this case, and you see that more or less you get that the coupling of weak coupling is more or less 10 to the minus 6 once you have set alpha s, the strong coupling, to 1. So you see that to explain this lifetime and this lifetime on very similar particle, you need to say that this particle does not go through strong interaction, but through a new type of interaction, which you call it weak, because the coupling is 6 orders of magnitude weaker than the coupling which is responsible for strong interaction. Okay, so just to set you the ideas. Okay, good. I see people smiling, saying yes, yes, pleasure. Yes, it's good. Okay, good. Okay, good. So this is a bit a sort of partial answer to many questions which was asked yesterday. Okay, now now next slide. In fact, I found this this plot quite interesting, and you can play a little bit. I mean, there was in some books that I think with a certain time with Marie-Hélène Sergei we tried also to fill up. But this shows the lifetime. In fact, is log of lifetime because in order to show as minus log, of course. This is minus 20 and so on. And this is the log, and this is P max is the space phase. I mean, space phase is the term in the previous transparency. Sorry, in the previous transparency. In fact, in a decay, for example, you can always use the momentum when you do, for instance, this going to that and that. Is the two P are the same in the rest frame, and this is the P, the momentum of these two particles in the rest frame. So it's a characteristic of the decay, because as much as your momentum is, somehow is reflecting that you have a lot of space phase in front of you. If this is very small, means that you have just few configuration open, okay? It's the same. I mean, you have a large, if a P star is large, means that you have a lot of different configuration if conservation laws allows you to go into decay. If it's very small, it's small space phase. So it's a good translation. This is a translation, that is mathematical translation of a space phase in terms of, by the way, it's clear. I mean, space phase depends on the momentum left to give to the decay particle, and this is just the mass, is square root of s, is the mass of the particle decaying. So it's quite obvious. I mean, it's quite evident way of seeing the space phase of the decay. So we go back to the next transparency. Yeah. Here you see that in fact you can somehow, it's quite clear that you see, okay, forget a little bit that, but you see at least that you have a bunch of particles which are here, where your lifetime is measured through the width of the resonances, and then you have particles which are here, which in fact you see the order of magnitude. These are weak particle, strong particle decaying, and these are weak particle decaying. Of course, in this plane of tau of lifetime is clear. Then it's important to put also that, because clearly, I mean, you can have, okay, this is a bit more complicated, you will see the interaction are not universal and so on and so forth. But then, of course, as much as, you see, as much as your phase space is, as short as your lifetime is. So it's natural that it goes like that, okay? So you have bunches of interaction, the three fundamental interaction, and then this is kinematics, which shows you that, in fact, if you have more phase space, you go quicker to decay because you have many more possibilities, just a matter of a probability. And the little here is the neutron decay, which is a sort of anomaly in that due to the very small phase space. Okay, good. So I think this is quite, let's say, setting mind plot or pedagogical plot when you want to look at that and the reason of different interaction. Okay, now so far so good. One interesting stuff also in order to setting the idea, because often people say, I mean, strong, weak electromagnetism, we know what it is, I mean, it's everywhere, I mean, and then even, I mean, okay, it's everywhere. And it's easy to find example of electromagnetism. Strong interaction again is the fact the nucleon stays together and so on. Weak interaction, often you say, okay, is a beta decay, and okay, when you want to think about where weak interaction plays a role, where are important weak interaction, in fact, it is the beginning of the reaction in the sun. In fact, the fact that the sun is burning and giving energy, and not only that, give energy, and in fact is a fantastic neutrino factory, is coming from that, from weak interaction. In fact, the sun reaction start from weak interaction and inverse inverse beta decays, because in fact it starts, okay, this is a bit long to say, but it's quite simple somehow. You have a proton inside a very dense core of the sun, you have in fact I mean, you can get proton-proton close, as close as you can. Then in fact inside the sun, this proton can even occur this inverse decay. I mean, you can have an inverse, and you can go to neutron. So in fact this is calculated inside the density of the sun core. This is a very rare process. In fact, the proton can stay stable 10 to the 10. Okay, there is a sort of inversion of the stability, but 10 to the 10 years before going dark. Then proton and neutron get together. They do to deuterium. So you have deuterium plus the positon neutrino, which are produced. Then, of course, the positon will find, of course, an electron playing around, because electrons are often there to play. I mean, positon sometimes is more difficult. And then they goes to the electromagnetism. So there is, in fact, the long lifetime of the sun is justified by the fact that this process is very rare. It's very difficult to reproduce in laboratory, and when you do the budget, the balance is 0.4 MeV. After the reverse beta decays, in fact, you have a gamma-gamma which goes, electron-positon which annihilate to gamma. Then deuterium and proton goes to helium-3. This is very, with the gamma, this is very energetic, nice budget. Then, of course, the best is when you go to helium-3 to go helium-3 and to P, because this is very stable, which goes to, I mean, when you sum up all the budget, is a very positive budget because it's for a single particle, so imagine how many there are. So, in fact, the sun is nice because in the sun there are, in fact, somehow we start with the weak interaction. You go on with the, of course, you have a strong interaction in fusion. Then we have electromagnetism, and then you have a positive energetic. So what you say that the reaction started thanks to the weak interaction, and you produce energy and gamma. And what is very interesting for gamma is photon which stay trapped, and then is global energy radiating by the sun. But what is just the other thing, if you start and you look at the neutrino physics, and you see that many discoveries have been done by using neutrino coming from one of the best sources of neutrino, which made possible some discovery like neutrino deficit and so on, neutrino oscillation. You always heard about neutrino from the sun. In fact, are exactly those neutrino we are talking about. Are neutrino which are coming from the first inverse beta decay of the sun. Okay? So just this was a sort of parenthesis to say that weak interaction plays and beta decay plays an important role in the production of energy of the sun. Okay, now, so now it's probably slightly more difficult the next slide, but I wanted to introduce the first theoretical idea on weak interaction before going to then formalization of the standard model, which will be done by Stefan this afternoon. So in fact, the weak interaction where the formalism start in the 30 by Fermi and was done in analogy with electromagnetism. Okay, so probably you're not, most of you, I mean at least the people from the third year of the university, you are not familiar with many of these concepts, the way of writing, of course, interaction in terms of current, coupling, and so on. So I will try maybe to a bit oversimplify the picture in order to give you ideas on that. But somehow is a quite important concept, which is also related to what Marie-Hélène yesterday did in terms of introducing new physics. So I try to put some pieces together in your mind, and I try to be clear also in explaining that. So in fact, QED somehow, okay, when you do QED, you can see it in terms of interaction. You can see in terms of interaction. You can see okay, this of course is not working like that, but I mean because this is okay. You do in fact. What did I put the problem here? I wanted to put more. Okay, it was. Because this is electron, neutrino, and the proton part. But this is already the analogy. Don't be confused by that. I mean, as I just said that when you do electromagnetism, you have in fact a part which is related to proton going to neutron and the other one electron and neutrino. Okay, this is the way I want to show that. Okay, this is just a transformation proton neutron neutron proton. Okay, okay, and then exchanging something which in general you can think is a sort of photon, and then the part which is electron neutrino. This is the way when you have a scattering like electron scattered to something else, electron at the end, is something like that. Okay, so the analogy which was done by Fermi was to say that in fact you can do something like that. I mean, you put a charge here and you put this propagator. Okay, propagator means that you have something which in terms of when you make when you want to make a contact between two lines, you have to transfer a particle which is a messenger of your interaction. Okay, in case could be a photon or other particle if you want to introduce new interaction. So you have also to think that new interaction somehow are just to put new particle translating. I mean, this could be another particle. Okay, so as yesterday I said, when electrons scattered with electrons going giving a photon, that you have electron, or you can say two electrons meets by exchanging a photon, and then they change their direction, and you have two electrons in the final state. Okay, so here somehow you can try to do the same by saying, can I extend this formalism by saying that the proton, but in this case should transform in neutron. So of course this line is not the same, because in this line you cannot exchange a gamma. And then
you have a picture.
Yeah, okay. Okay, this one. Okay, this one is the correct one, but the analogy was starting from this one. Okay. So somehow what you pay in terms of electromagnetism is that you have a coupling, which is the charge, and you know that you have also the q squared, that is a transverse momentum, which is the price to pay, or is something which is there when you propagate something. So you have to propagate this vector boson, this particle, these messages, which allows to connect the particle which are in the final state. So you pay in terms of a coupling, which is here, and in terms of 1 over q squared, which is in fact the transfer momentum. Okay, the way that electromagnetism is with just 1 over q squared, in fact is due to the fact that the particle which is exchanged, in fact, is not massive, is a zero mass particle. Okay? When you try to do the analogy, in fact Fermi proposed in fact to have a local interaction. Instead of saying, okay, that you have this exchange, he says that in fact he tried to put an effective coupling, saying weak interaction are in terms described as electromagnetism, but in fact is a sort of local interaction. It's like if this you shrink like that, so you arrive to this configuration, and you say that in fact you have a sort of interaction like that with this point, which somehow, before you don't know what is exchanged, you say my coupling is an effective coupling, which is, of course, at the end, when I will find the right theory, would be the fundamental high-dimensional coupling divided by something which is energy squared, which normally, if you have this, could be q squared minus mass squared, but the mass squared there was 0, so it's a sort of effective coupling which has dimension Jeff minus 2, is dimension energy minus 2. For a moment, I just don't know what is taking place there. Of course, you can see that as much as the particle exchange is large, as much as this interaction is point-like, as much as the range, you remember yesterday, when I threw a big ball, the interaction is close and the range is close, and so it's a sort of a contact and local interaction. So this is the basic fundamental idea. So now, if you go to next, I think, no, next is too much. No, before. Right, okay. Okay? It's okay. So now maybe now there are too many details that I will also leave in the slide. But Of course, if you want, for instance, to calculate many different, okay, there is some consequences. I mean, somehow, I want just to say two things that maybe you can just try to keep in mind. That when you have the right theory and when you go to the standard model, normally you like to have constant interaction coupling, which are without dimension. Okay, and the value of that give you the strength of your interaction. Then you see yesterday from LAL that are evolving in time, when the energy is very high, they evolve. Okay, it's a running constant. But normally there are not dimensions. When you have a coupling which has a dimension, just think deeply to that. Is normally because you don't know exactly your interaction. So things to about electromagnetism, if you have two stuff like that and you communicate, you have to write that in terms of coupling divided by the propagator. And in the propagator you have the transfer momentum and the mass of the particle which is transferred. Okay? So that means that you can keep the high dimensional coupling and you know the propagator and the mass of the propagator which is responsible of interaction. Okay? On the other hand, if for the moment, for the energy scale you are, or because you don't know exact theory, you can in fact condense that in a single point, and your coupling has a dimension. When a coupling has a dimension, is normally an effective theory, is not the fundamental theory. Okay? Ta-da! 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 No? More or less? So another way of saying that an interaction can be weak or can be strong before the coupling is weak or strong. But another way of having an interaction weak is also to have a messenger which is heavy. Okay? There are these two conditions. Is G divided by the mass essentially proportional? Okay? So there are these two. But normally this comes from the fact that in the propagator you always associate coupling divided by Q squared minus M squared of the boson which is exchanged. Okay? So now, if you want to make some practical dimensional argument, you see that when you do any coupling now, even when you do any coupling like that, okay, or you just do that in this way. So this is the point-like way, and this is the when you are good enough to resolve the fact that there is something which is exchanged. Okay, of course, when you use the coupling here, this coupling will go as a G squared. This was the Fermi constant. Okay. Then, of course, you can, when you make this calculation, for instance, you do muon decay or neutron decay. Of course, as soon as you put G squared, because in this case you have a G squared, of course you have to put, just for dimensional argument, you have to put an energy to the power 5, because G squared is Jev minus 4, energy minus 4. You have to put energy 5 in order to have a dimension energy, which is the dimension of the width. Okay? Just very simply, you know that many of your decay width cross-section will go with the terms which will be proportional to something which is energy power 5. Okay? So in case of muon decay, it would be the mass of the muon because we are in the decay. Okay, in this case is more expressed in this way. Okay, but this just if you have time, just to look at that. That for instance, when you measure very precisely the muon lifetime, you can get out of this measurement a value of the G Fermi constant. And in fact, G Fermi constant comes out to be 10 to the minus 5, J minus 2. So you see that in fact, to explain the fact that this has a lifetime which is 2.2, 10 to the minus 6, so 2 microseconds, in fact, it's explained in terms of a constant which is ordered 10 to the minus 5. Okay? Okay, remember, if you go to the real first transparency, when I start from, is more or less that. Okay, in order to explain these decays, you get more or less something which is order 10 to the minus 5, 10 to the minus 6, in order to explain why these lifetime are so short. Okay, so this is okay, we go back. This is somehow the main message I want to give you. Okay, so now I think the rest is a bit too many details, so you can go on. So I mean, this is just another example showing that weak means also very weak cross section. I did for you an exercise. If you have time, you redo it. So you see that in fact the cross section of neutrino against electron is 10 to the minus 44 centimeter. Okay, so it means, for instance, that if you have a neutrino 1 MeV, it will live in LED 24-year light. Okay, so this is just because weak is weak. Weak is short lifetime and very, very little cross section, like this value, which tells you why neutrino, which occurs only with interaction, can travel and pass several times through the Earth and so on. So this is the concept of being weak, right? In terms of cross section and weak. Okay, go on. Okay, go. Okay. This somehow is the idea. Okay, as soon as you find the right theory, you pass from G becomes that. Becomes in fact the idea of saying, okay, but this is not a contact, an effective theory, but in fact what is going on here is just that you emit a W, and so you have a propagator which is this form, and this, your constant here becomes G divided by that. Okay, so now if you go on, I want to okay, go please. Okay, so also here there is some detail. This is all in preparation of what we will learn from, then we will present by Stefan. Again, you can take again another example, so it's still a repetition, but from that I want to show you an important concept of why the weak interaction is weak. Okay, so here you take the two way of seeing muon decay. You can say muon decay like muon emitting a W minus going to neutrino and then coupling and going to electron neutrino. This somehow is the modern way to see a muon decay. Muon decay alla Fermi is like that, is a contact. This is a muon current, okay, the muon current. Here is the electron current, and here this W is just a blob which takes into account the coupling and the fact that you exchange some particle, eventually massive particle. So if you go in this way, so if you do alla Fermi, you do, okay, there are some numerics because this is not anymore, okay, the progress also between Fermi and the standard model that we realize that the weak interaction is not a vector interaction, but is V minus A interaction. So only left component of the particle participate. This is a degree of complexity which eventually we can discuss. But forget for the moment that. You make a calculation of your matrix element, and you find, in fact, that these, apart some numeric, which are important, of course, which is G divided by square root of 2. This is the coupling here. While the coupling here, we will see with the Stefan, is given by a fundamental coupling, and of course, when you suppose that the Q square is much, much less than the mass of the W, is given by that. Okay, you can neglect that, and you get just 1 over n. So you see the transition between the view of a contact Fermi interaction and the view of weak interaction is given in this way. So in fact there is this clear relation, okay? This clear relation. Good? So you can relate the coupling constant of Fermi with the fundamental of standard model coupling and the mass of the W. So this formula gives you exactly all the concept I tried to give you. So that as soon as you find the right theory with the exchange of a W boson, you can get that. Okay. Now if you do now simply numerics, okay, you see that you can, out of that, to know the mass of a W. Okay? But of course, you have an unknown there, which is the strength of the weak interaction. Now, suppose that you have find a fantastic theory which does tell you that the electric charge and the weak charge are exactly the same. A big unification, somehow. I mean, you say my theory, then Stefan will discuss quite a lot of that, I hope. Yes, okay. He's saying yes. You say, okay, I do my unification, I put gauge theory. At the end, I can show that in my G is equal to electric charge. So, great. So, like you know very well that, you know an example in the past, no? In the past. Magnetism. Magnetism, which is the difference between electrical and magnetism? Everything is governed by what? By charge. But the phenomena are completely different, no? Where the difference is coming from? Huh? Moving charge. I mean, the strength of the strength of magnetism with respect to the electric charge is static and moving. But you know that when you move, I mean, you can see electrical or magnetic in exactly the same way. And this is great unification, this electric charge. But when before you were discovering electromagnetism with pole, we can also think that was a different coupling played there. But then by doing this coupling, you have to integrate maybe the speed of light in your coupling, which was an effective coupling. Not at all. Q, E, and Q, V, cross B. I mean, and then you know that in relativity is exactly the same. Okay? So here we have exactly the same case. Electromagnetism was a great unification. Now you want to make a unification of eventually weak and electromagnetism, which will be the lectures of Stefan, and E. Eventually you can say, great, I find that G is equal to E. Okay? Then if G is equal to E, okay, this is publicity for Stefan, and at the end, by saying that the mass of the G is equal to 10 to the minus 5, measured by the muon lifetime, you would find that in order to do that, you need a W which is 37 GeV. So in fact, the two interactions are fundamentally the same, but the weak interaction is weak just because the W is heavy. Okay? Okay. In fact, this is the point. I mean, somehow you can say unification of forces and so on, but at very low energy, when Q squared is much less than the mass of W, so beta decay, all the decay which are at our scale, NeV scale or even less, not many GeV scale, we can electromagnetism are the same. In fact, you will see that this unification, unfortunately, is not so perfect like that, but you'll see that the electric charge would be G sine of theta Weinberg. Okay? Okay? You will see that unification, that there is a relation in the standard model which tells you that this is the value of the relation between electric charge and weak charge. In fact, unfortunately, they are related, but are not exactly the same, and they are related by another free parameter of a standard model, which is an angle, okay, which will be introduced by Stefan. Which just, when you do that, in fact, the mass of the W, once you measure that, you will end up even higher, which is 80 GeV. In fact, was the way this was foreseen at the beginning, and this is where the W was searched by the CERN experiment. So, just to conclude this part, even since this value is that, less than 1, even the electric charge is smaller than the weak charge. The weak charge, the weak coupling, is stronger than the electric coupling, but the weak interaction is weak because the boson exchange is heavy. Okay. So this is a sort of a tremendous theoretic plus experimental which gives you really how things are going. So weak interaction is weak because the mass of the exchange particle is heavy, and then okay, then of course also the range of this interaction is very short because you remember Heisenberg delta E times delta TH gives you that in fact is a fraction of 1000 Fermi. Okay, is a very close encounter, which somehow is just translating that when you are at a very low energy transfer, momentum transfer, in fact this theory works perfectly because the mass of the W is so heavy that when you look at a phenomenon at 1 MeV having an exchange boson of 100 GeV, in fact you can very well approximate by an effective theory. Okay, good. Okay, so okay, this so pay attention when in fact in the lecture of Stefan you will move from the perfect unification to the partial unification, and which is given by that. Okay, so standard model cannot predict exactly the coupling, but can make relation between electro-weak and the electro and the weak coupling. Okay, good. Now. Okay, this I was preparing that by thinking. Okay, but it's exactly the same thing as I said before. In fact, often you introduce a new scale or new something. When in electromagnetism you do that, you say that in fact the electric charge, you could say that the electric charge is different from magnetic charge. Okay, but you know that in fact the magnetic effect become important when the velocity become large and they are in case comparable with the electric effect. So it's the same. You know that here electric charge and magnetic charge are the same. This is unification is just perfect. Okay, it's a simple way of seeing. Then if you do it with the relativistic formalism, it's just great, perfect. It is a very simple equation, but it's exactly the same. Okay, here. Okay. Here, unfortunately, we were not so perfect like this because in fact E is not exactly equal to G. Okay. Now, okay, just I'm finishing the lectures by saying that okay, so far we always said W, W, W. Okay, but W you see is charge. Charge means that you change, I don't know, up quark, which is 2/3, in -1 quark, which is d bar, and so on. D bar to d bar. Okay, so it's charge. So it's a charge part. So you will see then that in the formalism, which is SU2, and you need 3 boson and so on. But just if we go on more experimentally, there was a big effort in the 60s and then in the 70s when it becomes possible to have a neutrino beam. Neutrino beam, you have it normally by strong proton interaction in the target, you have kaon in pi, and then for instance here you have neutrino mu, because you have decay of pion and kaon in neutrino mu and mu. Or you have a neutrino electron out of a reactor out of intense beta decay sources. Okay? Then it becomes possible to start to study the neutrino beam. Now, if you take a neutrino beam and you know that the neutrinos interact weakly, you see that you have a laboratory which gives you, when you have this decay, neutrino and mu, exchanging W, for instance, you have this part is a hadronic part and a W going to neutrino and mu. This is what we call charge current. Because charge current, because this is a W which couple, you have at the end a charged particle accompanied by a neutrino. Of course, this kind of reaction cannot be mediated by a photon. It's clear, okay? Because these are neutrinos, okay? So in fact, if you have this kind of reaction, you should have a companion, a neutral companion of the W, okay?
Okay, this experiment, this would be a sort of neutral current. In fact, what I'm just telling that historically, the Z0 was found like that. In fact, you will see that weak interaction are not only mediated by W, charge W, plus and minus, but there is also a companion which is neutral one. And the way it was seen, that normally in all neutral current, since the photon electromagnetism is at that scale an interaction which is stronger than the weak interaction, all the processes which can go through the electromagnetism dominate against the weak. So it took quite a lot of time in order to be able to say that there was a mediator which was not a photon, but in fact the neutral part of the weak interaction. We need to have neutrino to do that. Okay? So now if you see the next slide, in fact this is, was a big discovery. Okay, this is very difficult to interpret this, this event, but in fact it was observed an event where in fact a neutrino, antineutrino beam was occurring against an electron, give again a neutrino, an electron in the final state. In fact, this was the track of an electron which was seen. And this was a big discovery, or the first, would say, indirect discovery of the presence of a new particle exchanged in this loop. Okay? So in fact, in the 73, the Z0 was somehow discovered or introduced in order to explain that out of, you threw neutrino in the bubble chamber, and at the end, in the final state, you have just an electron. And the way of explaining this reaction was not possible but by using this, which in fact somehow was expected, because you have W plus and W minus in interpretation for weak interaction, and you need again this, this particle in order to explain that. So out of that, you thought that you have W plus, W minus, Z0, okay? 3 vector bosons in order to explain a weak interaction, and few years later, in 76, the standard model was formalized, and then these were in fact the 3 vector bosons which are out of SU2 symmetry, gauge symmetry, okay? But this was the way it was introduced, okay? Introduced and discovered. We discovered a little bit before. Now, if we go just to the end, okay, we go. Okay, I think that at least before the discovery of the X in this century, I always thought that this was one of the greatest discoveries of the previous century. So we are lucky that we are in between the 2 centuries, so we can really indicate, okay, even millenary, no? Because I mean, changing millenary. But this was really, for me, this is a success of intellectual, incredible success of intellectual. Because again, you can always say, okay, we introduce somehow a particle which are responsible of interaction, okay? But these particles which are responsible of interaction, we always introduce in terms of virtual particle, okay? We say that, I mean, you have a photon, but then we say weak interaction is the same. With interaction, you have dust. But in order to explain that, I mean, with all formalism, will be done a bit by Stefan, you say, okay, but this you should have a W which is exchanged in order to explain. Then, of course, this W should be heavy, because if it's heavy, of course, the weak interaction is weak. Same, you do neutrino physics, and you say, okay, to explain mu going to electron, you need a Z0. Also, Z0 should be heavy in order. At a certain point, you have almost prediction out of the standard model that these particles were there, and they were about, in the case of W, 80 GeV, and in case of Z0, 90 GeV. And even we know that the relation of the mass between W and Z was even predicted by the standard model through, again, this parameter, which is the Wick-Weinberg parameter, angle parameter. Okay? So, in fact, means that these particles are virtual in the interaction. But as soon as you have the energy to produce them, they are real particles. Okay? So again, it's like the drive-in. Of course, you can be very far from that, and they still W and Z, and you pay an enormous price to pull them out of the vacuum in order to contribute to the interaction. So you like that, like, but and then they are responsible for interaction. But as soon as you have the energy to produce them and to be on shell, you have to see as a particle. So matter, interaction is exactly the same thing. I mean, is particle, they should give spectrum, they should give a resonance, okay? So they are real particles, okay? Then again, weak interaction is weak because you are at very low energy and you have to make an enormous, you have to ask to Heisenberg a lot of credit. Because, I mean, you go to the bank, you say, come on, I need $1 million, but I am only €1. He says, yeah, but I'll give you back soon. I say, very, very soon, I mean, immediately. It's the same. You have to borrow a mass of stuff, like that, and then the bank says, give me back the money. And this is delta T, immediately. Otherwise, you go to jail. Okay? So it's good. So it's the same. So this is the reason because the weak interaction is weak. Because your empreinte, you have to ask this and you have to give back immediately. So it's a short, is a range, and then it's extremely weak because it costs a lot to do it. But as soon as you have at the mass a 90 GeV, we learn from standard model that the G is equal to E almost. So weak interaction is not weak anymore. And then we have to see as a particle. Okay? So somehow this plot and this plot somehow translate that. So you see a Z0 and you see a W. Okay, this is less good because W goes often to go often if you go to lepton, there is a neutrino. So when you have to reconstruct the invariant mass of the W, is less precise because you have a neutrino you don't reconstruct. But you see mass peak. So you see 90 GeV. Okay, this is not 80 because the neutrino is not reconstructed, but it's compatible. Okay, but look to that, this is more clear. You see Z0. So as soon as you have the energy to reconstruct the Z0, Z0 is a particle on shell. On shell. When, in fact, you use it for weak interaction, Z0 is over there. It's the long, long tube and tail of the Bragg-Wigner of describing this particle. Okay? But otherwise, it's a real particle that you can produce. And LAP and so on were factory of the Z0. You put yourself, you construct a machine, which is called LAP in Geneva, where all of us work, more or less work, the old people work, and you do E plus E minus, and you set E plus E minus exactly at 91, 90, something GeV in order to produce a lot of Z0. And at the end, in this machine, we produce how many? All 20 million, no? 20 million Z0. So, from standard model 76, Z0 in Gargamel, neutral current 73, discover in CERN in 84, 10 years later, we construct a machine in order to reconstruct like 20 million of Z0 as soon as the energy is there. Okay? So interaction particle are particle that can be seen as a particle, as a resonance, as soon as you have the energy to do it. And with that, I stop. Okay, thanks.
Thank you very much for the brief